Okay, hello people. We don't need this, we don't need this. Okay, hopefully the machine will handle the load and it will not affect the recording. We are going to continue understanding why SkipList are such an efficient data structure. Why does give us the insert and delete and find all in logarithmic time? In most cases, when it does it, it's really quickly. It's log with small constant before it. So we'll talk about this part, then I'll show you a proof that is actually rigorous about how unlikely it is to find really bad skip lists. And then we'll play with a few homework / exams questions as time permits. Before that, any questions about material from yesterday? The skip lists, stuff that I assume most of you knew, depending on the preference of whomever taught you 345. So, I want to convince you now that the expected time to perform insert and delete and find is order of log n. And here I really need to be careful about what is expected. Expected, say, is average life, but on something that is randomized, and no problems. No problems at all. And the first part of the talk is a proof, and then we'll do our homework. Okay, so I need to tell you what does expected here means, and think about it this way: we have the same set of keys x1, x2, x3. Xn. These are the keys, and we are to be inserted. I'm going to insert these keys into the skip list, and as I'm inserting each key, let's say always with the same order. And after I created the skip list, I perform find or delete or insert for some element, and then I kill the skip list and do the same thing again with the same keys in the same order. What might be different? The coins that I tossed. Right. And this coin affects, of course, the running time. We already discussed it. If all the elements appear only in the lowermost level, then we have nothing better to do. Then it's just a normal linked list, and there is nothing better to do than check each and every element once at a time in order. If all the elements appeared in the topmost level, it's even worse, because then it's both very bad time and very bad memory. So we need somehow the balance, but the algorithm for determining for an element in how many levels it can participate was nothing but let's keep trying tossing a coin until we got a fail. And the number of coin toss that we had to do until we got a fail is a number of levels that a new element participates in. So I keep making the same experiment of rebuilding the same skip list, re-performing search again and again and again. I did it a million times. Each time I have the time for insert or the find. And it takes the average after all the construction for the very same input, but different type of coin toss. So that's much stronger statement than saying only if the input is really friendly, only if the input is uniformly distributed, and I cannot handle a malicious adversary. So that's not the case. We want to say no matter what how bad the keys are. People over the internet, if you are experience lagginess, please let me know. I'm kind of, you see, I'm kind of squeezing a thing that OBS takes. on the effort. It might create lagginess. Okay. So let's prove this hand wave proof this claim that insert or delete or find will take. And now for insert and delete, actually, the time is the expected number of elements that scans during the findings. Let's understand this statement, especially that I think that I need to delete it. How does the insert or delete looks like in a skip list? I start from the top element. Top element send me to an element of the skip list at the very highest level, that send me to the next one, send me to the next one. In the highermost level, I scanned a few elements in the top level. Finally, I move down a bit, continue scanning several elements in this level, went down a bit, and so on. And finally, when I get to the lowermost level, then I can perform deletion by removing a few pointers, but how many? Only one per level. I'm sure that the number of pointers that I removed in the delete was only once per level, while the search might have visited many elements in the same level. Same for insert. The insert of a new element over here, say, would involve inserting a new pointer in each level that this element participates in. But what took a long time is presumably finding this element again, because of the reason that we spent a lot of time in the very same level. The skip list does not guarantee that you will visit only one element per level. So let's see how many elements are we expect to visit, actually. So during the find operation, I started maybe from the element B, that was the very first, the highermost, leftmost element of the skip list. Maybe I started from B, and that's because level R+1 is the highest level. Possibly this is the case. Possibly the case is that I somehow got to B after a search path. That is, there are levels that are higher than the level R+1. I don't care. Either way, I got at some point to level B, to level R+1, visiting element B. I don't care if I got to it from the left or from the top. And now my question is, my scenario is, I considered B, and from B, all this during a search path for an element that I'm trying either to find or to delete or to insert, of course. I got to B, and from B, I moved to one level down to level R, from R+1 to level R. And here in level R, let's assume that I'm spending a lot of time all the way when I'm searching for the element X. X is a new element that I'm trying to find, to insert or to delete. So I spent a lot of time in level R, moving from an element to the next one, to the next one, to the next one, and then finally maybe I found X, maybe I moved one level down. But I'm trying to argue that sure, it could be that we'll visit a lot of elements in one level. It could be, but no, it will not be common. It will not happen frequently. When we are building our skip list, that this case has low probability, or very low, or very, very low. How low is this probability will be depending on what we mean that I visited a lot of elements. The more elements I visited, the less likely it is to happen. Let's try to make it more formal. I visited B, from B I move down to B1, and then I move to the right all the way up to, say, B8. I visited 8 elements all in this level. On my way to find X. And my question from you is first to notice that all these elements are all smaller than X. Right? I'm only moving to the right. Remember the if or the skip list. You're moving to the right only if the next element is still smaller than X. You never overshoot it. Okay, so B1, B2, B3 are all smaller or equal to X. What can you tell me about C over here? Remember, I visited B and did not move into C. How come? C. Had C be small or equal to X, then from B I must have gone to C. I'm trying to stay in the same level for as long as possible. On the other hand, I saw that C is overshooting, is too large, meaning that I had to go down because C is larger than X. What is the maximum level that B2 participates in? I know that it participates in level R, say the first level, but how do I know that B2 does not participate in level R plus 1? Maybe it was promoted to level R plus 1 as well. No. Why? Because B2 is smaller than X. B2 is smaller than X, and had it been promoted also from level R also to level R plus 1, then from B I would go to the right into B2. Conclusion, B2 participate in level R, but not in level R plus 1. And same goes for B3, same goes for B4, B5, B6. All the elements that I scanned in level R, none of them made it to level R plus 1. Now let's think about the insert process that I used. B2 for B2. I tossed the coin a few times. It was quite lucky to make it to level R. And then I gave B2 a 50-50 chance to move it also to level R plus 1. Once you make it to one level, you have a 50% chance to be promoted to the next level. So B2 had its chance, but decided, no, I'm not going to make it. I got a fail about promotion from level R to level R plus 1. All agree? Had it been participating level R plus 1, then our search would have visited B2, but B2 did not make it, for sure. Same goes for B3, same goes for B4. All these 8 guys, none of them was promoted to the next level. And then I'm asking what's the chance that you'll find a run of 8 guys that all you toss the coin 8 times for each one, in different times, of course. You had plenty of other experiments. But at some point in the history, you toss the coin 8 times, once per each of the 7 times for each of the elements from B2 to B8, and all of them fail. What's the chance that this here happens? Well, the chance that you get a fail for in one trial is 50%, is half. The chance that it happens 7 times would be, of course, half to the power 7. One over 2 to the 7. That's the chance that you, during the find, you'll have to visit 7 elements. What's the chance that you'll have to visit even more elements in one level, say 10 elements? Then this probability goes down to be 1 over 2 to the 10. 2 to the 9, because one element I had to visit anyhow. So it's the other one. So it's 1 less. What's the chance that you have to visit 11 elements? 1 over 2 to the 10, which is about 1 over 1,000. So, quite well. Okay, so that was a hand wave that tries to convince you that it's quite unlikely that in the same level you'll have to visit a lot of elements. Maybe you'll visit 1, maybe 2, maybe 3, but it will be rare to visit many more. So on average, you can say in each level you're spending a constant time. Now, we also argued yesterday that the number of levels is log n. Where did this log n comes from? Because we saw that in level 1 I have n elements. On average, I have n over 2, n over 4, n over 8, n over 16. After log n many levels, I'm running out of elements. So we are putting these two claims together. In each level, you're spending about a constant time. In each level, you're spending about a constant time. The number of levels is log n. Voila. So the expected time, number of elements scanned per each level is order 1. Again, it's on average, it can be higher, but the probability of being higher decreases exponentially. There are log n levels, so the total time on average is log n. Okay, and that summarizes the intuitive explanation. Let's try now to dive a bit deeper to understand why the SkipList behaves so well. And we can pick a few parameters of the SkipList, and the simplest that I could pick and still give a rigorous proof would be, let's talk about the height of the SkipList. And I'm saying we have about n, we have exactly n keys in level 1, and half n over 4, n over 8, etc. But this argument is, and at some point I'm running out of elements, and presumably it happens after log n many levels. And you all feel the right intuition, but I am trying to convince you, or I need to give you a concrete bound on how likely it is that you'll see many more levels, many more than log n. So what log to the base 2 then would be the height of the SkipList if it is a perfect SkipList. Now, you can limit the number of elements artificially, but in my code I don't do it. So I can say don't go over too many levels outside. Don't increase the number of levels by more than 1 or many more than log n, but it doesn't necessarily will make your code any faster or number of elements any smaller. You could, it's not bad, it's not a bad heuristic, but as you'll see in a moment, it's not necessary. So, log n levels, log to the base 2n levels, that's what I expect to see, that's what I hope to see. Otherwise, actually, performances are degrading. I'll ask you what's the chance to see a SkipList that has 2 times log n. Like our currency now becoming log n. I expect to see 1 log n, perfect. 2, of course, the more elements in the SkipList there are, I expect to see more it to be of higher height, just like any normal tree. But so our currencies that we are depending on, log n is enough. Let's talk about how many coins each worth log n I'll have to pay. Maybe the height of the SkipList is 2 times log n, maybe 3 times log n, maybe 4 times log n. Let's try to understand what's the probability to meet a SkipList that has, say, 7 or 8 or 9 times log n. So I drew a little target on the whiteboard. I drew a square, my pathetic attempt to draw something that looks like a square. Its area is 1 meter by 1 meter, and inside it there is some shape that I'll call A. And I'm tossing a dart out there, and I'm sure to hit the square, and I'm asking each point on this square has exactly the same probability that I'll hit it. Each point, I'm completely uniformly distributed inside this square. What is the probability that I hit A? What is the probability that my dart hit exactly A? The probability that the dart hits A is just the area of A divided by 1. But if A covers 50% of the square, then my probability of hitting A is half, my probability of hitting outside A is half. If it's 30%, then 30% of the area. I picked this square to be of area 1. Each point has exactly the same probability to be hit. So all uniformly distributed. So I'm just asking what is the probability that I hit A? And you can say that's a chance that your dart landed in A. And if my dart landed in A, we'll also say, abusing notation a bit, we'll also say that event A happens. If I hit A, I'll say event A happens, or just A. If my dart hits A. Not much surprising so far. I didn't say, hopefully, anything controversial. Here is another shape, B. And I'll ask what is a probability. I'll abbreviate it by probability that B happens. B happens meaning that my dart hits B, or abusing notation that event B happens. And again, the answer is area of B. And area is not a good word in English because it means both how many square centimeters there is inside as well as the region itself. Here I mean the region of the how many square centimeters there are here, again divided by 1. What is the probability that I hit either A, my dart hits either A, or that my dart hits B? My dart that landed in the square, it hits either A or B, which is just the probability of the union of these two regions divided by 1, as before. I'm asking, what is the probability that I hit inside the area that is not white, either the green or the blue, or the area that is both? Well, so, a lot of you have seen this formula before. How can I know what is the region in the union? It will be the region inside A plus the area inside A, probability that I hit A, plus the area inside B. Let's count it. It's all the green, all the red area, plus all the blue area. But when I do it, I overcounted the intersection between them. I overcounted the intersection between them twice. So say the area of A plus the area of B minus the probability that I hit both A and B with the same dart, because I counted the intersection right. probability of A intersection in B is a probability that my dart happens landed in the intersection, which is just how many square centimeters I have in the green region. So far, I don't think that I told any of you something new, but here I'm going to say this intersection counting deal starts to be messy for me. Because it's fine if I have only two shapes, A and B, as in computer, talking about the intersection is fine. But if I'll have three objects, A1, A2, and A3, A, B, C, then now to compute exactly what is the probabilities they hit either A or B or C, I need to start counting it's a sum of the individual areas minus the intersection of the pairs of them plus the intersection of all three of them. And if I'll talk about even more shapes, start to be hairy. So I want to say, you know what, let's just approximate. It will be sufficient for our purposes to just come up with a bound that is sometimes useful and sometimes not. So I want to say probability that I hit either A or B, possibly both of them, back to the two, is, as we said, probability of A plus probability of B minus probability of the intersection. This number is positive. This number is positive. This number is positive as well. So if I take from this term and not subtracting this positive number, not subtracting it, I'll just get an even larger number. So I'm erasing the probability of the intersection and saying the probability of you hit either A or B is smaller or equal than the probability of A plus probability of B, and I don't have the correction term over here without a minus. Of course, if they are disjoint, then this bound is actually tight. That's exactly the probability. But if they are not, then it's complicated. But it's still true. Similarly, if I have A, B, and C, probabilities that I hit either A or B or C is not larger than probabilities that just A happens or probabilities that just A2 happens or probability of only A3. The sum. Quick example of other tax events. In a roulette, American roulette at least, you're getting the result of a number K, which is hopefully uniformly distributed between 1 and 38. You can declare the probability of A to be, when you're using the roulette, the number that you hit is even. The number that you hit is even. Between 1 and 38, there are exactly 19 even numbers. So 19 over 38 gives you probability of 50% that your event A happens, namely you hit an even number. Let's define as event B the probability that the number that you got is divided by 3. 3, 6, 9, 12, etc. There are 12 such numbers between 1 and 38. So that's actually the probability. 12 over 38, about 0.3. What is the probability that either event A happens or event B happens? Possibly both of them. That is, the number that you got is both even and divided by 3. This probability is smaller or equal than, just sum up these two numbers, which is 0.8. Possibly it would be larger than 1, and then it doesn't give me much information. What does it mean that it's smaller than 1? It's always smaller than 1, so it's not always informal, but it's not always giving you extra information, but it's always correct. back to our skip list. How could it be that I have a really tall skip list? How could it be that I have a skip list of size 10 times log n, or size 5,000? No. Remember how we'll do, remember the insertion algorithm. Each element on its own pick a number k, and this number determines the number of levels that this element participates. And if the number of levels was larger than the previous number of levels of the skip list, I just built more levels to accommodate the newcomer. So what I want to ask is, are there any really annoying elements that kept tossing the coin forever, creating many levels? It is possible that X5 created so many levels that it creates a really tall skip list by itself. Maybe it happens for X5 that it wants to be very tall. Maybe it happens for X3 that it wants to be very tall. Maybe X1 is an annoying guy, etc. So to have a not too tall skip list, to have a normal size skip list, it means that none of the keys, not X1, not X2, not Xn, none of them doesn't want to be in so many levels, in ridiculously too high many levels. That is, look at every value of k that you have in mind. K equals 17. We always like 17. How could it be that the height of the skip list is larger than k? It could happen only if X1 said, I want to be in more than k levels, or X2 said it, or X3 said it. One of the keys must have said, I want to be in so many levels. Let's meditate on X1. What is the probability that X1 participates in more than k levels? How did I insert X1? I told X1, you're 100% you're in level 1. Told the coin, you have 50% chance to be in level 2. If this happens, you have 50% chance to be in level 3, and so on. What is the probability that I got more than k, or at least k levels for X1? What's the chances that you have k successful coin toys? We've got faith in all of them. This number happens only if to move from level 1 to 2, which the probability is half. To move from level 2 to 3, probability is half. Probability is half. This happens k times. Right. You, in all these consecutive trial, when you inserted X1, it wanted to keep being promoted. So the probability that X1 participates in more than k level is small or equal, write it down, probability that X1 is in more than k levels is small or equal to 2 to the minus k. Should be minus k over 1. You know, minus just means 1 over 2 to the k. So that's the probability that X1 participates in more than k levels. But maybe X2 was the annoyance that participate in so many levels. What's the probability that X2 participate in more than k levels? It's exactly the same number. 1 over 2 to the k. 1 over 2 to the k. 2 could be corrected to k minus 1. I don't want to make these indices too complicated. and so on, all the way to xn, the last keys that you are inserting. Now I ask you, what is the probability that any one of them decided, what is the probability that at least one of them decided to be in so many levels? It's just either it happens for x1 or it happens for x2 or for x3 or for maybe two of them or for maybe three of them. But as we saw in the previous slide, I can just sum up the probability. This number is smaller or equal than the probability that it happens only to x1 plus the probability that it happens only to x2 plus the probability, and so on. Just sum up the probability to each level, which gives you what? There are n keys. For each one of them, the probability was 2 to the minus k, was 1 over 2 to the k. So the overall number is n times 2 to the k. Take L, everybody with me? This number, n over 2 to the k, is a probability that at least one of the numbers wants to be in more than k levels. Now, if I take k to be just log n, then I'm not getting much out of this number. If I take it to be exactly log n. So let's take number that is a bit more interesting. So just repeat the same argument. Once again, just different slide. For the probabilities that x1 participate in more than k plus 1 level is 2 to the minus k. I can call this number a1. The probability that a1 happens, that x1 is so tall, is 2 to the minus k. And the probability that each one of any of the aj's, either x1 or x2 or x3, it happens to, it is 2 to the minus k. Summing up all these numbers, you're just getting n times 2 to the minus k, 1 over 2 to the k. This is exactly, or this number is a probability that the high of the skip list is more than log n. It might be overshooting, might be too large. Okay. Therefore, the probability that any xi participate in at least k level is, as we said, n times 2 to the minus k. That's the height that means that the height of the skip list is at least k plus 1, ignoring the k. Now let's play with a few facts that you know from elementary school, probably. Which will be, take any three numbers, y and y to the power of a times b. Y to the power of a times b is just y to the power of a, all the way to the power of b, or I might as well write it as y to the power of b to the power of a. And I want to mention a few other things. 2 to the power of log n is nothing but n. And 2 to the power of 5 times log n, it is nothing but, what did we say? I can switch a and b, making it 2 to the power of log n, 2 to the power of log n, switching the 2. What is 2 to the power of log n? It's just n, to the power of 5. Okay, we're ready to put it all together. Now I want to ask, what is the probability that the height of the skip list is z? Z will be 1, 2, 3, 4, 5 numbers that I'm going index of something, times log n. What's the probability that it's 2 times log n? What's the probability that the height is 3 times log n? 4 times log n? Oh, second. Okay, we're all ready to put it together. the probability that any xi's participate in at most k level is this number, smaller or equal than n times 2 to the k. Fantastic. What's the probability, therefore, that none of the elements wants to be z tall? The probability that none of the elements wants to be z tall, and that's why the SkipList is nicer, will just be larger than 1 minus this number. Coming up in a moment. I'm going to use this number to tell you that the chances that this crucial event of very tall SkipList is extremely slim. Like really, really, really extremely slim. Let's do it. It's just a bit moving elements from time to time. So I want to ask, what is the, I'll take this k and I ask, what is the probability that the SkipList is more than n times? And k I'll just write as log n times z. Z I didn't decide it. It will be 3, 4, 7, 5, 10 at most. So what, let's write here n over 2 to z. K will be log to the base 2 times n. So what is 2 to the k when I write k at this point as coins of log n? It's 2 times log n times z, 2 to the power of log n times z, which is switching the z and the log n. You have 2 to the log n, all of it to the power of z, which is n to the z. So what is this number? This number is just n over 2 to the k, which is n over n to the power of z, which is just 1 over n to the z minus 1. Okay, here I have n to the z. N divided by n to the z makes it 1 over n to the z minus 1. And we are done because that implies that that's the probability that you'll meet, or that bounds from above, the probability that you'll meet a SkipList whose height is z times log n, z times log to the base n. Or in other words, the probability that your SkipList that you meet is not of this type is 100% minus this number that is going to be really, really small. Let's play with number. Let's assume that I only have 1,000 keys, because this number, of course, if I have more keys, even better. Let's say that I only have 1,000 keys and I build a SkipList. What's the probability that the height is larger than 7 times log n? Probability that it's more than 7 times log n is putting the number small or equal than 1 over n to the z minus 1. Z is 7, z is 7, so 7 minus 1 is 6. The probability that the height of the SkipList is so large, much larger than log n, is smaller than 1 over 1,000 to the power of 6, which I think is pretty small, 10 to the 18. You want to push it even further? What's the probability that the same SkipList has height that is even larger, larger than 10 times log n? This probability is smaller than 1 over 10 to the 27. You can see, implying that the probability that the SkipList does not have this height, has lower height, better behaved, is larger than 1 minus this really tiny number. The chances that you'll get a lightning, hit by a lightning, or being hit by lightning is much higher than the chances that you'll find a SkipList that is not well behaved. Okay, makes sense? So I'm trying, and that's a completely rigorous proof. I did not put any details here under the table. That's exactly how you bound the probability, but also see the math tricks that I did. I said I want to know, going back a few slides, I want to know what is the probability that the skip list is too high. But for this, I need to ask what is the expected probability, and now I have messing up with a lot of variables, and I have no idea how to compute it. So that was too complicated. Instead, I said, what's the for a single element, what is the probability that the single element, the single key, what's the probability that the single key is misbehaved? That was easy to compute. It was 2 to the minus k, just like 1,000 points. And then, and that was a new trick that I introduced to you, instead of asking for one single key, I ask now what is I ask for a bound, not for an exact number, but for a bound on the board, and how are the chances that any of these guys is bad? And I tell the probability that any of these guys, maybe more than one, but any of these guys will ill behave is smaller than just n, the number of keys, times sum up all these numbers. And what we showed is that this number, despite being multiplied by n, this 2 to the k decreases so fast that even when you are summing up all these numbers, you're getting something really tiny. And it's really useful technique. Okay, questions? Excellent. Let's play with some homework. Sometimes I'm using it for homework, sometimes using it for the exam. Yeah. Okay, so what I want to show you in a long sequence of questions, applications, is that now when we know how to use a skip list to find or insert or delete a key, there is many other things that I can do. I should put it in the chat so people can access it more easily. Just sending it. Chat. I just sent it, this file over Piazza. So you see a skip list here, but the skip list is augmented. The skip list is augmented by adding, sorry, Anthony, I see your answer now. ADB. So I take the skip list, I augment it so it can help me find more information. And usually when we are talking about augmented skip list or augmented data structure in general, let's add fields that can do something and store information, and this field will see what type of information I'm getting. So in this particular example, what you see is that every node in this skip list, every node stores a key as normal skip list, and these keys are appearing just like in normal skip list. The leftmost one is key minus infinity, next one 6, 8, 13. You see here is another element with key 13 pointing to each other, as they should. Key 18, and so on. So the keys are arranged in the skip list normally, and usually every level is a sorted linked list. Every level is a sorted linked list, as usual. But I also it stored a key. I don't know how to call it. The key is in a field named key. But I also, every node, let's call it every node V, node V stored a key, let's call it V dot key. But it also every node V stores a key V dot size, where V dot size equals to the number of keys between V dot key including to V next, to V next key, not including. Fine. I think that it was the most obscure sentence I ever wrote. That if you're using V dot key including to V dot next dot key not including. So first, for this node V, what is V dot key? It's just minus infinity, just to make sure that the notation is clear. V dot key for this node is minus infinity. V dot key for this guy would be 6. V dot key of this guy is 22, and so on. Now, what is V dot next? The V next key. V next key. Just an example. V next key of this guy is 13. Is a key value of the next guy in the same level. It's a key value of looking at the node V. Remember, don't confuse. V is not a key. V is not a key, and it's not sorted. V is a node in the skip list. It's a disk like this. V dot key is a value stored right here. V dot next is a next node. V dot next dot key is a key value. If V is this guy, then V dot next key is 18. If V is this node, then V dot next dot key is this one. Is the key of this one, which is 40. Okay, now hopefully everybody understands what this term means, what this term means. Let's now try to encrypt what I wrote over here. What the including means is I'm asking how many keys there are, including this guy. That's the including. And when I'll talk about the next guy, I'll say I'm not counting this one. And now you can all understand hopefully, all understand what does v dot size should store? V dot size of this node will ask how many keys do I find between, how many keys can I find between myself and the next one in my level? When you're counting, don't count the next one, but do count everything up to the next one. So I'll count how many keys in the skip list are between this guy to this guy. Answer 1, 2, 3. The next one is already not included. Okay, that's why v dot size of this node would be 30. Would be 3. Sorry. Can you see it at the end? The 3 over here. That's 3. What about this node? What's the next of this node? This one. How many keys can I find between this guy to this guy? 1, 2, 3, 4, 5. 6 already not counted. That's why the size here is 5. What's the size of this guy? How many keys are from here to the next one, including this one, not including this one? 1. Right. This one, last example, would be, I would say the size here is 4 because from this guy to this guy, not including this one, I'll have in the whole skip list, not in my level, the number of keys, not the number of nodes. From this guy all the way to this guy, I have 1, 2, 3, 4. That's why the size is 4. And now I'll ask you guys to use these fields and am I seeing correctly on this side? Yeah, it's readable. Yeah. How is the quality in the Zoom?
It's not that bad, average.
Okay. And you know, on Twitch, the live stream is better, except that I don't see your chat on Twitch. But, yeah. So size counts the number of keys at the lowest level between the current key to the next key. That's absolutely right, Anthony. The number, and as you said, and I'll just highlight it, is the number of keys which stored in the lowest level between the node and the next key, but important, the next key in the level of the node. So the next node of this one is this one. The next node of this one, even though they are with both the same key, the next node of this node is this one, because they are in this and this are in different levels. Okay, so my question to you is, you are given an augmented skip list, augmented just in this way. So I already built it for you. You don't need to worry about building it, and explain how to perform count of explain how to perform the operation rank of X efficiently. What is rank of X? Rank of X returns the number of keys in the skip list which are small or equal than X. So if X is the smallest element in the skip list, then its rank is 1. And the smallest array is only one element that is smaller or equal to me. And if I'm the last, for the largest element in the skip list with 140, the rank will be n, because that's the number, I'm the nth smallest or n largest number in the skip list. But I'm the nth smallest. I'm not the smallest, I'm not the second smallest, I'm the nth smallest. I'm just counting, if I sort all these keys, how many are there? So the operation rank takes X, X is a query. We use the word query a lot in this course. It means that I spend my time, maybe during peacetime, I have a lot of time to build my data structure. So I'm preparing my data structure, and maybe I can do pre-processing that will optimize the data structure in some sense. And now after I build the data structure, I face a query. And this query is one out of many. You're going to bombard me with a lot of queries, and the idea is that each query I'll have to answer efficiently. There are queries appearing all the time. They're part of the process, and there are many of them. And rank of X is, I'll give you a number X. It's a query number. You don't know it when you build the skip list. I surprise you with a number, 17, and you should tell me how many keys there are that are smaller than 17. And you can do it in a few ways. You can say, I'll start counting from the lowermost. Right? I'll first find the element that is a leftmost, smallermost one, and then go to the next, go to the next, go to the next, until if I ask what is the rank of 43, eventually you'll get to 43 when you are going linearly, and of course then you know this number. So that's what the rank, and I'm asking you to do it more efficiently, of course. And I suggest at this point that I'll break you to say, how many guys? You guys will start talking, and I'll see if we have enough to break you to rooms. So I'll break the Zoom into 2 rooms. So we'll try to break. Breakout room, and I'll just split you into 2 rooms. Let's see how it goes.
We can discuss it.
So I'm thinking about going to like number level.
It's like less than 18.
So to the next
So
one.
we can go down there.
And then check the size on check. So it's going to be cheaper. And that's what's going to skip some of these ones.
Yes, so technically it's searching for the key, or we need to have some sort of key where you add the key.
Have the size.
The key point is goes just like some search and match, just like skip a log. You kind of the same, but you count every time that you're going down, you count downward. The one that wants to because the one before going down, you count up to that.
Yeah. Did you load yesterday?
Yeah.
Was it like really
Is it possible to
Okay, how many are we in this room?
The dot next one is let's get the figure out. Yeah.
Yeah.
I think it's not
looking at the slides from last year's teacher or
Yeah.
previous teacher. It seemed like that person, whoever it was, their slides were like,
Yeah, he's really good.
yeah, I forgot what it is there, but their slides were really good, so far as the previous. So, since it is short,
longer
to come back, right? Even we can use the double concept. The key point is that if you start from the numbers where to start from,
Okay.
it is efficient, then you know which is the
Okay. People, if I can also see your faces, would be fantastic. The ones in the gallery. And share with me any thoughts with Jake, Rachel, Anthony. I mean, I'll give you another minute or two, and then I'll ask somebody to form the. People in Zoom, you're more than welcome to use your voice, except that I cannot. Amir, can you try to speak via the Zoom? I'm not sure if I can hear them.
Can you hear me?
I cannot.
Oh, my phone should be outside.
So can you take out the green
Yeah, it seems like there's no speaker. Let me put the
Yeah, it only works for
but at least you can hear.
for level story. It could also.
It's okay. Use my laptop as the speaker for students to talk.
What's the difference between level 1 and the other ones?
Oh, there's loop. But please don't. Oh,
Because now I can hear you. Jake.
oh, it goes
both
through
sides
this
of
one.
it.
Yeah, it goes through this one. Okay, let me think how to solve this.
Indeed. Nice job, Jake.
How to turn on the.
Okay, Jake nailed it. Jake has a good answer. Anybody else wants to chip in? What are you suggesting?
Whenever you go to the next, choose to go to the next one, you add the size, you keep the size count.
I'll keep a counter. So I'll keep a counter initialized to base 0, count equals 0. And I'm going to perform a very normal find. But as I'm performing the find operation, find of x, as I'm performing the find operations, I'm looking at the path that I'm traversing. The path that I'm traversing will either, at a node V, the path that I'm traversing will either branch or continue branch to the right, or my path branches down. But at every node, as I'm looking around, my path, I'll either decide to continue to the right. When do I continue to the right during the find? I'm just performing a normal find. I compare v dot key of, say, this node. Is this still smaller than x? And if actually I'm looking at the next key, at the next v, I'm at this node, asking for the next node, is a key of this node is still smaller than x? If yes, then my path will continue to the right. If the condition is no, then my path will go down, maybe one level, maybe more. And so on, and that's how schematically my path looks like. Now, what do I do with this counter? What do I do with this counter? If I reached this node, call it W over here, if I reached W and decide to go down, I don't change the counter. So I don't change the counter at W. Nor do I change it at A over here, at this node again, because I went down. On the other hand, what about U over here? I decided that from U, I'm moving to the next element. My search, where I perform find of X, remember, that's X over here. The value I want to find its rank, but to do the rank, I'm just performing find of this guy. Here I started from the minus infinity over here and decided, say, to go to the right, which means what? I just jumped over a bunch of keys. Which just means that my counter, each time the path branches to the right at node V, we perform counter, and to the counter the value of V dot size. So if during the find I branch to the right at this node, it means I know over how many nodes I skipped over, and they are added into the count. And I'll do it every time that I'm going to the right anywhere along this path, and just return count at the end. Make sense to everybody? People, make sense? Excellent. Now I want you to tell me, how much time does it take? Well, depending on the skip list, but if the skip list is well behaved, which is almost always the case, then it's log n. It barely changes the time of the find. Now, I want you to find a different query, same condition, different query. Report ranked K. K will be is an integer which is between 1 ... n, and what I ask you is find a key in the skip list whose rank is K. It's just the opposite of what we had before, just a mirror image. My previous query of just ranked gave you a key X, and I ask you how many keys are there that are before X. Now I'm switching the rules a bit. I'm giving you a number, k, and I want to know out of all these keys, who is this number? For example, if I want to ask you who is a median, I'll ask you what is a find rank of n half. The median is an element that has n half many keys, smaller than it, and n half many keys, larger than it. Make sense? So find rank of n half should return the median. Find rank of n should return the last element, and so on. And again, I'm asking how to do it efficiently. And the conditions about it, and the conditions are the same condition as in the before. That is, you have a skip list that is so nicely arranged and nicely placed. Yeah.
There's a question from Zoom.
In the chat, yes. Don't we have to do? You mean as an answer to the previous question? The rank will.
Yeah.
Yeah. Oh, finally I hear it. Yeah. The rank will be the same. Right. The last element when I got, oh, you mean when I got? You don't see. Did I miss part of the? I'm just rearranging the OBS because you don't see part of the whiteboard. You mean when I got to this very last element, I check for the very last element if it should be counted or not, because I didn't say that X is necessarily one of the keys. It doesn't. For the previous query, it doesn't matter if X is one of the keys or not. I just return the number of keys that are smaller than it. You're right that if I were well correctly, I might have counted or not counted the very last element where the very last key where my search ends. If I would have defined the rank as the number of keys which are strictly smaller than X, then that's fine. If I want to tell you how many keys are smaller or equal to X, then I need to decide if I reached X or reached somebody that is larger than X. If that's what you meant, then I would. But then I have to define the rank as the rank of the first node is 0, so it looks a bit unequal. Okay, back into rooms.
Yeah, the size is larger. We look here, right? It's smaller. We go down a little. Same thing on the next level.
I mean, you want to join the other room, and there is one room that I joined to. Check the other one. And, okay, Victor, G, I get, and Zai. Yes. What do you think? So the question was do you guys not see the whiteboard board?
Yeah, the right side we can't see.
The right side, what about the right side? Now you see the right side. All the way up to, okay, I see. All the way up to,
Oh, okay.
and the idea is, of course, understand the question, how to perform this find. How this time I want to use procedure similar to this find, change it a bit, of course, so that I'll ask you who is who is the element in the 10 percentile? Who is the element that has exactly 10% of the keys smaller than it? And you can report it in login time.
I mean, there are only levels, right?
So, any thoughts?
Go like once and go down once for each level, and so that will be longer.
Who are we? We are with Victor. How should I pronounce? K-I? Chi?
GAO, Gal.
G. Okay. Oh, Tony. That would be easier. And Zai. Guys, any thoughts? The idea is, of course, to use these size fields somehow.
Check a little bit.
So the hint is, of course, to use the same size field. What? To use the same size fields and to decide using the size field and to decide using the size field. Yeah, it's a bit tricky. Using this size field. Let's say that guys, can you see in my room? Can you see my what I'm pointing to?
Yeah, size 4.
Size equal 4. Let's say that I'm looking for the third largest element. I always start my search from here. Let's say that I'm looking for the third largest element. Elements that are three small, that are two elements smaller. Can the size field tells me should I go to the right or should I go down? I'm looking for the third largest element, and I'm asking for this guy, should I go to the right or should I go down?
Just the key, just how you search for the key.
So right.
Counter, which is
If I go from here to the right, it means I'm jumping over four keys, maybe 1, 2, 3, 4. I jump over 4 keys that I have no way to retrieve. They are back in the past.
You don't know which key you're searching for.
So I cannot go back to them. So if I'm looking for the third largest key, then my path from this element should go down. Yeah. So the hint is make a decision from the root, the top leftmost key, if you want to go down or you want to continue to the right, and see if you can continue arrange this algorithm to converge to something.
If you skip forward, right? So you
Okay,
can say that
let's close the room
key
if I succeed.
You already skipped 4 keys on this key. And if you go down, I mean, it doesn't matter if you go down because you have the key right now in this level. Let's say you're searching for something like
Oh,
Okay, so
I can go.
I'm sorry. Yeah. So yeah.
You're searching for 10.
Mhm.
You just go down because itself is 10, and at the end is you're knowing that the key of infinity, it has 10 keys at the end. If you're searching for like 8,
Yeah.
you skip 4 up to here, you skip 9 up to here, and then you go down. You should go down because 9 is larger than 8. And then you go up to here, it's like 7. And then up to here, yeah, you just need to go down again because it's 9, and then you just search up to just cumulative number.
Okay, yeah, so we have 3 minutes, so I'll just finish it up. I heard the correct voices from all over the room and all over the web. Here I'll start when count. I'll start my algorithm when I'll set count to be this number k. The number k that I picked for you. I'm looking at the very first node, and I'm asking, should I proceed to the right or should I go down? If I proceed to the right, it means I'm jumping over 4 keys that I have. I don't want to revisit, I don't want to go to the left. If I jump, I'm jumping over 4 nodes. Let's say if count will be 7 in my example, then the answer is sure, you can afford counting, jumping over the first, the next 4 keys. Why? Because we know that they are all smaller. I'm looking for an element that are 7 keys smaller than it. And if I'm jumping over the 4 smallest keys. So whomever I'm looking for, let's call it the median, maybe I'm looking for the half element. The median is not one of the very first 4, so I can afford jumping from them. So now I proceed with my search after I jump to the right, but now I'm looking for an element where there is no, beforehand I was looking for keys that are k elements smaller than it. Now I just put aside 4 of the 4 that I just skipped revisiting, which means that now I'm not looking for the k value. Instead, I'm looking for the, if I branch to the right, then count equals count minus v dot size. This v dot size are not count. Why did I decide to go to the right? Because count was still larger than the number of elements I'm going to skip. So if the counter is larger than the v size, then jump to the right. You can afford it, just update the count by counting, by looking for an element whose rank is lower. It's now the rank not among all the keys, but only among the keys that are left to the, only among the keys that are to the right of where my mark is. So if count is larger than v dot size, move to the right. If count is smaller than v dot size, example, I started when count is 3, but v dot size is 4, implying that if I'll jump over the 4th largest, which is exactly what I'm looking for, then you cannot jump to the right, branch down, and continue from here recursively. But maybe I said it in a very convoluted way. Hopefully that's what everybody gets. And it's again log n. Finally, what's so nice about this v dot size is that I can also insert and delete. You work a little bit in the homework, but you can also insert and delete. And how do you insert a new element? Just everybody that you're visiting, every relevant counter, you'll just increment by 1. So it barely changes the time for the insert. You're just adding an element to whomever you visited, and similarly in the deletion. There are a few details that you easily discover at home, but insert and delete also takes log n. So to summarize this whole augmentation deal, I can answer ranking queries. I can answer tons of other queries as well. I can ask you what is the average key in some way. I can ask you who is, I can think about it as a bank account and think about what was my balance at different time, because now it's summing up, not exactly the rate, but I'm summing up something else. Again, you'll figure out the details. It doesn't change the insert and the delete, or change very little, or doesn't change the big O of the insert and delete, and of the file by itself, and it's very convenient for many, many other operations. So this augmentation is really useful trick. Okay, we might not have an in-class meeting on Monday, and I'll prepare a lecture, a recorded lecture just on Monday. Tuesday, etc. We are continuing as normal. I'll send an exact announcement if it happens. Just this Monday. So in this case, we will not have. People, any questions about the solution? People of the web? Any questions about the second query? Everybody understand how this count? It was, I didn't give you exactly the pseudocode, it was a hand wave, but essentially you're using count and either going to the right, and if you're going to the right, you're just decreasing the numbers that you jump over from what count used to be. Decrease a number or don't decrease this number if you're going down. And that play a bit with the details, but it's just how I'm dictating the search when I decide go to the right or go down, go to the right or go down. Hopefully everybody is good with this. Questions? Excellent. Thanks. Later. Bye.